In this video, we're going to look at three different perspectives of using the first and second derivative. And these three questions are all FRQs taken from previous years. So the first example is what we would call a numerical representation or tabular. So notice I'm given a lot of values about my function in a tabular form. I'm told that it's continuous on a closed interval, and it's also twice differentiable. So that means the second derivative does exist, except at x equals 2. And we can see that at x equals 2, both the first derivative and the second derivative do not exist. We have properties in the table above. D and E includes the derivatives of f do not exist. Okay, great. Now the first question is asking, so in the interior of 0 and 4, what are some relative extrema? Well, we know relative extrema occur at critical points. And critical points are when the derivative is equal to 0 or the derivative does not exist. So I'm going to look at my table and look at the derivative line, and I'm going to see when is the derivative 0 or doesn't exist. So we can see that a critical point is at when x is 1, because we have a first derivative of 0. And then another critical point is right here at x equals 2, where it does not exist. Now, in order for it to be a maximum or a minimum, then that means the first derivative, so I'm going to make a first derivative sign chart, has to change signs prior to 1 and after 1. So if I look again at the first derivative line, and I look prior to 1, the f prime x is positive. And after 1, it's positive. So then this is not an extrema because the sign does not change of f prime. Now the second value at 2, when I look at the sign chart of f prime, the interval prior to 2 is positive and the interval after 2 is negative. So this is, actually it's a maxima because I'm increasing and then I'm decreasing. So we would say then that we have a maximum at x equals 2 since f prime of x, d and e, and the sign of f prime of x changes from positive to negative at that point. Okay, great. Now let's go on to part B. Now part B is we're going to be looking for points of inflection. Well, we know points of inflection occur when the second derivative, remember points of inflection, we always look at second derivative, when the second derivative is equal to 0 or d and e, and then it must change signs. So this time I'm going to look at the second derivative row, and we can see second derivative is 0 when x equals 1, so we'll investigate that. And then second derivative does not exist at x equals 2. And then we can also see the second derivative is equal to 0 at x equals 3. So we must check out the sign charts for the second derivative at these points and look to see if the sign changes. Well, at 0, prior to 0 it's negative, then it goes to positive, so that will be a point of inflection at x equals 1. Now at 2, prior to 2, it's positive and then goes to negative. So again, we have another point of inflection. And then at 3, we're going from negative to positive. So we have a third point of inflection. So the 3 points of inflection, now if I probably should write the ordered pairs, it's going to be 1, 0, and then 2, 2, and then 3, 0. Sorry, my 3 doesn't look much of a 3. Are points of inflection since concavity changes at these points. Okay, great. Now let's go to the last part, which I know you're going to love. Now in this problem, we have to sketch a possible graph of f. Woohoo! So when I make my xy axis, I'm going to have an x value of 0, an x value of 1, an x value of 2, and an x value of 3. And I'm going to start by graphing the y values for each x value. It makes it kind of simple. So I'm going to graph 0, negative 1, and then I graph 1, 0, and then I graph 2, 2, okay, and then 3, 0. Now, on letter A, we learned that at 2, we have a maximum. So I know I'm going to be increasing and then decreasing. Now, also, we look at the second derivative and we can see concavity, right? And so we can see it's concave down between 0 and 1. So it has to be concave down. And then it's positive from 1 to 2. So it must be concave up. Okay? And then it's going to be negative from 2 to 3. So it's going to be concave down. Okay? And then it's going to be positive from 3 to 4. So then that will be concave up. Now I'm going to adjust this a little bit. Wait. So concave down, concave up, concave down, concave up. Does that look about right? I think so. Wait, concave up, concave down. Yeah, it just looks kind of funky, huh? So basically my shape kind of goes like this, like this, like this. Whoa, that was ugly. Like this. Okay. Yikes. Okay, anyways, good enough. Moving on. Now we'll be looking at using the first and second derivative test, but this time taking a look at what if we're given a graph. So we're told right here we're on the closed interval, negative 3 to 4, and we are actually given 1 point on the original function, 0, 3. And we can assume that we have a line segment and a semicircle. Well, knowing all of that, let's answer the questions. Where is f increasing? Well, we know f is increasing where the first derivative is greater than 0. And according to the interval, the first derivative is greater than 0 on the interval negative 3 to negative 2. Now, find all values of x for which f assumes a relative maximum. Well, we know maximums will either occur at the endpoint, so we have to consider those. And our endpoints are negative 3 and 4, and then critical points, which is when the derivative is equal to 0 or when the derivative does not exist. So looking at the graph, are there any values on f prime that have a value of 0? So we can see here at negative 2 I have a value of 0, and here at 2 I have a value of 0. That's when f prime equals 0. So negative 2 and 2. Now are there any values of f prime that do not exist? Well, we can see the whole function is continuous of f prime. So f prime is continuous on the entire interval. Now you may say, but wait, Ms. Kleiber, what about at 0? Well, you're kind of thinking correctly, except for it's the derivative of f prime. Like if I took the derivative there, because that's a kind of a corner cusp, then the derivative would be undefined. So in other words, f double prime is undefined there. Okay, so now we've got 4 possible candidates for our extrema. Now since we're given the first derivative, I'm going to use a sign chart to help me determine what's going on exactly at those values. So my endpoint's negative 3. I have a critical point at negative 2, a critical point at 2, and another endpoint at 4. So the first derivative is positive in this interval, negative on this interval, and negative on this interval. So a possible sketch would be it's positive, negative, negative. So you can see we have a maximum at x equals 2. And our justification, x equals negative 2. And our justification would be, since f prime of x is equal to 0 at x negative 2, and f prime of x changes sign from positive to negative, we therefore have a maximum. Now see, where is the graph f concave up or down? Well, for concavity, we always look at the second derivative, which is the slope of the first derivative. So where is the second derivative greater than 0? Because then this will be concave up. So in other words, where is the slope positive? Well, we can see that the slope is positive actually only on one interval, from 0 to 2. So on the interval 0 to 2, our graph is concave up since f prime of x is greater than 0 on that interval. Now where is it concave down? Well, that will be when the second derivative is less than 0. And where is the slope of the first derivative negative? Well, that would be on every other interval. So from negative 3 to 0, and then union with 2 to 4. And this is where the graph is concave down since f double prime of x is less than 0. Now we got one more. Okay, this last part here is 3 more questions on the exact same graph. Find x coordinate of each point of inflection. Well, we know points of inflection occur where the second derivative is equal to 0 or the second derivative is not defined. And we already talked about that the second derivative is not defined at x equals 0 because we can see there's like a corner cusp there, right? Now, in order for it to be a point of inflection, the sign of the second derivative has to change. So notice I'm labeling my sign chart. It's a second derivative sign chart. And to the left of 0, the second derivative, in other words, the slope of the first derivative, the slope is negative, and the slope to the right of 0 is positive. So yes, this is a point of inflection since concavity changes direction at x equals 0. Now, what about any other points? Well, we can see that the slope here, when x is 2, is 0. So another point that we need to investigate is x equals 2. So does the second derivative change signs at x equals 2? So I'm making a second derivative sign chart, and to the left of 2, the slope is positive. To the right of 2, the slope is negative. So we have a second point of inflection at x equals 2. My justification would be, since the sign of second derivative changes from positive to negative, and the second derivative is equal to 0 at 2, this is a point of inflection. Okay, part E, find the equation for a line that is tangent. Well, we all know for an equation of a line, we need a point. Yay, they gave me a point. And we need a slope. Well, luckily, they gave us the slope graph, right? Because they gave us the graph of f prime. So what is the slope at 0? Well, the value at 0 is negative 2. So the slope of f is negative 2. So my equation is y minus 3 is equal to negative 2 times a quantity x minus 0, which would be y minus 3 equal to negative 2x. Now the fun part, sketch a possible graph. Now you'll be using all the information we've answered from the previous questions. So I'm going to draw an xy axis, and I'm going to be going from negative 3 to 4. Now remember, it's the shape primarily that we're looking at because we're really only given one ordered pair in F, and that ordered pair is 0, 3. Okay? Now we did learn earlier that we have a maximum at negative 2. And when we look from negative 3 to 0, see negative 3 to 0, notice the slope of f prime is negative. So that means it's concave down. So it's going to be concave down on that interval. Now let's check that. See how the function's increasing, and it's increasing. And then when I get to negative 2, it's decreasing. And it's concave down the entire time. Now also we have points of inflection at 2 and another point of inflection at 0, actually just where I'm stopping, okay? So we have points of inflection. Now from 0 to 2, if you look at the graph of f prime, from 0 to 2, the slope of f prime is positive. So that means I'm concave up. So when I graph this, I have to make it concave up, okay? And now the last piece, you notice the slope of f prime is negative. So that means the last piece will be concave down. Okay, and we have an endpoint at 4. So my graph looks something like that. It's kind of an odd shape, isn't it? It goes like that, and then it goes concave up, and then concave down. Okay, interesting. This last problem is for those of you that still got some grit left in you, because wow, this is going to take some. So we've got a function, and we know that x must be greater than 0. So we have to find the first derivative. Well, I think it might be easiest if I rewrite this in power form. So we have k, sorry my k looked crazy, x to the 1/2 minus the natural log of x. So first derivative, then we'll use our product rule. So I get 1/2 k, and then it's x to the negative 1/2 minus 1 over x. Okay, great. That's the first derivative. Now, you know what? I'm actually going to keep it in power form because it's much easier to take a second derivative if it's written as a power. So for example, if I have k over 2 x to the negative 1/2 minus x to the negative 1. So do you strategically see how I'm leaving it in power form? So now when I take the second derivative, I'm just going to use the power rule. So I'll bring the negative 1/2 in the front. So it's going to be negative k over 4. And then it's x, and I subtract 1, so I get negative 3/2. And then bring the negative 1 in the front, so it's positive x to the negative 2. And I'm going to leave it like that because it didn't need said I needed to simplify. So now moving on to the next part. Now, there's only one part, but it's going to be brutal. Okay, so oh no, there's a part C, sorry. For what value of the constant k does f have a critical point when x equals 1? Well, we know critical points are when the derivative equals 0. So my derivative that I had was k over 2 x to the negative 1/2, and it was minus x to the negative 1. And we know this will be a critical point, so it's going to be either equal to 0 or it's going to be undefined. Now, it's going to be, though, let's do a little more simplification when x equals 1. So let's put a 1 in there, okay? So k over 2, and it's going to be 1 to the negative 1/2 minus 1 to the negative 1. Well, we know 1, square root of 1 is 1, so I just get k over 2. And then 1 over 1 is just 1, so it's minus 1. Now this will never be undefined because it's linear, so we're going to set it equal to 0. Because critical points equal 0. So k over 2 equals 1, multiplied by 2, so then k equals 1. So we'll have a critical point at x equals 1 when k is equal to 2. Now we have to decide whether this is a maximum or a minimum. So remember, max or minimums, I look at the first derivative. Well, my first derivative was right here, so I'm going to replace k with 1. So I end up with y prime is equal to 1/2 x to the negative 1/2 minus x to the negative 1. And so I'm going to look at my sign chart because the critical point occurs when x is 1. Now this isn't really neat, really clean. It's going to be 1 over 2 radical x and minus 1 over x. So we're going to have to deal with some fractions here. So I need to pick a number smaller than 1 but greater than 0 because x has to be greater than 0. So I'm going to pick an x that has a perfect square root. So how about let's pick 1/4. Okay, so 1 minus 2, square root of 1/4 is 1/2. 1/2 times 2 is 1, right? So I get 1, wait, no, that's not right. So I should just work this out. So it's 1 over 2 square root of 4, there we go, minus 1 over, and x is 1/4, right, you guys? So I get 1 over, radical 4 is 2, times 2 is 1/4, and when I take the reciprocal of 1/4, I get 4. So 1/4 minus 4 is definitely a negative value. Now let's pick a number greater than 1. Again, I'm going to pick a number that has a has a perfect square. So let's pick the number 4. So now I'm going to get 1 over 2. Oh, and radical 4 minus 1 over 4. And I realize what I did in the previous one, you guys. I'm going to fix it. 1 over 2 times 2 is 4. So 1/4 minus 1/4 is 0. So see, I picked a number too large. It's too far away. So I have to pick a smaller number. Okay, so this doesn't work. While I'm fixing this, let me go ahead and change the mistake I made here. Did you guys see my mistake? I'm sure you did. Right here, this wasn't 2 rad 4. It was 2 rad 1/4. And rad 1/4 is 1/2. Well, 2 times 1/2 is 1. So I end up with 1 minus 4, which is still negative. Phew. Okay, now we have to pick a number actually closer to 1. So let's just pick 2. So I get 1 over 2 radical 2 minus 1/2. Okay, well 2 radical 2 is going to be bigger than 1/2, so we are going to get a positive number. So therefore, since it's negative to positive, we know that we have a minimum. So our justification would be that at x equals 1, there is a minimum value since the derivative at 1 is 0 and the derivative changes sign from negative to positive at that point. Okay. Okay, part C says now we have to give it for a certain value of the constant k, so we don't know k. The graph of f has a point of inflection. Oh boy, we're going to have to look at the second derivative on the x-axis. Well, if it's on the x-axis, right, x-axis, we know that the y values are 0. But if you look at your second derivative, there is no y value. So how do we use that fact? Well, let's go back to the original. If y is 0, then I have k square root of x minus the natural log of x. So you can see now I could find a value of k in terms of x. So natural log of x equals k root x, divide by root x, so natural log over root x is equal to k. Now this will help me because when I look at the second derivative, which we got in the first part, the second derivative is, let's see, it was negative 1/4 k, and then it was x to the negative 3/2 and plus x to the negative 2. So you can see I have two variables, but now I can rewrite this in terms of one variable. So it's negative 1/4, and then k is natural log of x over x to the 1/2, and then that's times 1 over x to the 3/2. So you see I wrote x to the 1/2 on purpose because I'm going to use my rules of exponents. And then it's going to be plus 1 over x squared. So cleaning this up, I have a negative natural log of x in the numerator, and then it's 4. Well, x to the 1/2 times x to the 3/2, we add the exponents, so I get 4/2, which is x squared. And it's plus 1 over x squared. Well, this isn't so bad. So I need to make a common denominator, so I multiply this by 4 over 4. So I get negative the natural log of x plus 4 all over 4x squared. Now again, we were looking for when this has a point of inflection. So the second derivative, when will it equal 0 or when will it be undefined? So we see it would be undefined when x is 0. But remember the beginning? X has to be greater than 0. So we can't consider that. So then we must consider the numerator equal to 0. Negative natural log of x plus 4. Subtract 4, negative 4 equals negative natural log of x. Divide out the negative, 4 equals natural log of x. And then to undo natural log, we raise each part to the e. So then we get x is equal to e to the 4th. Phew! So we will have a point of inflection and x equals e to the 4th. But remember the original problem said find the value of k. So we know that k is the natural log of x times over the square root of x. So the natural log of e to the 4th all over the square root of e to the 4th. Well, we know this is base e, so this would be a value of 4 over e squared. So k must have a value of 4 over e squared so that we have a point of inflection on the x-axis. I told you it'd be brutal, but that would be a 9 out of 9.